In this video, we're going to look at the 3D coordinate system. So we're going to look at a few things. We're going to look at how those points actually are. We're going to look at what surfaces look like. And then we're also going to look at how to find the distance of a line and how to create a sphere in 3D planes. So the first thing we're going to look at is 3D space. So if we think about the Cartesian plane, the normal one that we have an x and a y, and it's on a flat surface. It's known as 2 dimensions. So we have our x coordinate and our y coordinate. When we move up to 3 dimensions, we're going to have 3 coordinates. We're going to have our x and our y, and then we're also going to be adding a z coordinate into there. So we have 3 axes. We have our x-axis, our y-axis, and our z-axis. Our x and y we can think about as being our horizontal axes. Those are the ones on the bottom. And then our z-axis will be vertical. That'll be going up and down. So we basically take our Cartesian plane, set it flat on a desk, and then we have the z-coordinate coming up from our desk, which gives us our 3rd dimension. So you can see this with the right-hand thumb rule. It gives you an idea of how your x and your y's and your z's are. You can shift this around. It just depends on which graph you're going to be using to look at it and to be able to actually visualize those three-dimensional points. So we have 3 different planes in our x, y, z coordinate system. We have our xy plane, which is the basically the floor of my graph, or the desk if we're looking at it in that terms. We have our xz plane, which is the surface that would be made by the x-axis and the z-axis going up and down. And then we have our yz plane, which is made by the y-axis and the z-axis going up and down as well. So those could be considered the walls. Now, our coordinate system that we normally deal with, our Cartesian plane, we have 4 quadrants. We have and we go around the origin. Well, when we're looking into the 3 dimensions, we have 8 parts, and they're known as octants. So the first octant is just like our first coordinate or first quadrant, is all the positive values. The x, y, and z is positive, and then it goes around from there. We do the positive ones on top, and then the bottom 4 are the ones where the z is the negative values. So 3-dimensional graphs are very hard to visualize sometimes. We see it in space all the time, but to actually be able to draw it on a piece of paper and graph it out is very difficult. So sometimes it's nice to actually think about it, look at it literally as a room. So we have our left wall as our xz plane, our right wall is our yz plane, and then the floor is my xy plane. So, and then this is just a little bit more about how the x-axis and the y-axis rotates there. Now, our points in the plane are going to actually have 3 coordinates. We have our x, our y, and our z. So we're going to represent them just like we did with the points, at the parentheses with our x, y, and z coordinates in there. These are all going to be real numbers, so no imaginary numbers or complex numbers, just real numbers for right now. So in this situation, when we graph those points, we have our x coordinates first, then our y coordinate, and then our z coordinate. So when you graph it, you're going to do the same way that we'd be graphing it on our Cartesian plane. We graph the x, the y, and then we're going to go up from there to get our z. So we're still only going to have one point, and that point is P, in the actual graph. Another way to visualize it is actually a box. So we can actually look at all those connection points to that place, and as you go back and forth, we can see those intersection points with the planes as well, where we have the zeros on certain parts of that graph. So here's a couple points illustrated. We have -4, 3, and -5. So on my x coordinate, I'm actually going backwards on the x, so that's the negative side. And then I'm going on the positive side of the y, and then I'm going to go down 5 for the z. So that's -4, 3, and -5. 3, -2, and -6. I go 3, so I'm going to go positive. I'm going to go forward on the x-axis. Then I'm going to go on the left side on the y-axis, the -2. And then I'm going to go down again, -6 in this situation. So that's how we would graph in 3 dimensions. Next, we're going to look at a few surfaces. Now, if I was just to have a x equals or a y equals in the two-dimensional plane, I would just get a line. We have y equals 3, we have a horizontal line where y crosses 3. If I have x equals 5, I have a vertical line where x equals 5. However, when we're dealing with three-dimensional, when I have just one value, say I have z equals 3, that means my x and my y term can be anything they want. So instead of actually having a line, I have a surface, or I have a plane. And that is going to be parallel to the xy plane, because the xy is the ones I don't know. So the xy is parallel to where z equals 3. So I don't have a line, I actually have a plane in this situation. And the same thing as if I had y equals 5. In this case, I have y equals 5, and that's going to be parallel to the xz plane. And it's going to be 5 units to the right of it. Finally, we're going to look at the distance formula and how to draw a sphere. So the distance formula, if you remember from our Cartesian system, the xy, it's just you subtract the two x points and you square them. You subtract the two y values and you square it and you do the square root of it. It's Pythagorean theorem. Well, when we're looking at it in 3 dimensions, it's just expanded. All we're going to do is we're going to add in the z coordinate. So you subtract the x's, subtract the y's, subtract the z's, square each one of them, add them up, and take the square root of it. And that's going to give you your distance. So it's not much different than when we're doing it in the two-dimensional plane. It's very straightforward, very simple. If we look at a sphere, if you remember right, the formula for a circle was the basic formula, if it was centered at the middle, was x squared plus y squared equals r squared. If we shifted it, that's where we had the x minus h squared, and then plus the y minus k squared, and then equals the r squared. So if this is a sphere, I have 3 dimensions. It's going to be the exact same setup. I'm just going to shift it over, and I'm going to add in the z. So I have x minus h squared plus y minus k squared plus z minus I or l squared equals r squared. So the r is still there. It's still all squared. It's not to the third power. It's still squared. And that's going to give me my formula or my setup for a sphere. So that's the equation of a sphere. And if it was centered at the origin, I would just do the x squared plus y squared plus r squared equals r squared. So it's basically just a simplified version of it.